I'm Hongyi, and this is Ruihang. Our project is about deploying large language model to mobile phones with memory offloading. So, first question, why do we want to deploy large language models on mobile phones? There are two primary reasons. The first is data privacy. Because running on local mobile phones does not need to pass data to remote servers, so you can protect your privacy. And also, another reason is the ability to run offline. Say you're somewhere without internet and you need to ask AI a question, then you can do local deployment and you can run the element on your phone to get the answer. And there are two reasons to make this practical. First is mobile phones have powerful computation resources for ML deployment. Like for our iPhone or Android phones, they all have GPUs, and even for some Google phones, they have TPUs, and this will largely accelerate the computation of large language models. The second reason is that so our group have a universal deployment engine called MLC LLM, which allows deploying the LLMs on platforms ranging from large cloud server GPUs to edge devices. We have been maintaining this framework for a long time, and this proves to be a very efficient and very good platform for the deployment. But there's a problem. Every mobile phone have a memory limit, so some iPhone even have only 4 GB for each application. The latest phones have 6 GB, but it's still quite small relative to the total model weight. So for very small LMs, say Q1 306 0.6 billion model, it's easy to deploy because it naturally fits on the phone's device memory. But for large LLMs, say 4B or 14B, we cannot naively deploy it on phones. For 4B, we can use quantization. It's already supported on MLC. But for 14B, even using quantization, it still takes 8 GB memory, which is larger than the available device memory on iPhone. So the question is that, can we run LLMs that cannot naively fit on mobile phones? So we use a technique called memory offloading. Modern LLMs are based on transformer architecture, which consists of identical layers. Because our phone can only fit part of the layers, we can divide the model into multiple stages. And before we run a stage, we fetch the weight of that stage and evict the weight of previous stage. So by doing this, we only need the memory that equals the memory size of one stage instead of the whole model. So this is equivalently treating the phone's device memory as a cache for the flash storage. We implement the weight offloading technique through a compiler approach. So first, we add a stage boundary to the model definitions in MLCLN. And the next step is to transform the stage boundary into a call, into a function call, which evicts the weights of the last stage and loads weights of the next stage. And in this project, we have encountered some challenges. The first is that mobile runtime is hard to debug. Since there's no Python environment on mobile phones, there's no tools like PyTorch, Hugging Face, transformers. So we do not have a reference implementation and cannot compare our results. However, fortunately, thanks to ML compilation, we can test correctness on our Mac GPU before deployment of the mobile device. And then the implementation can naturally be transferred to the iPhone. The next issue is that in in MLC LLMs implementation, the copy of weight from flash storage to GPU memory includes three stages. First, copy from flash storage to CPU memory, then copy from CPU memory to some temporary CPU buffer, and third, copy from that temporary buffer to the GPU buffer. So this is indirect and time-consuming. We did a memory optimization for this. Since the iPhone have a unified memory means the CPU and GPU memory are the same. They have a unified address space, so we can directly copy the weight from flash storage to GPU memory without any intermediate buffer. So this reduces the memory cost, memory capacity cost, and also the memory copy time. The third is that our GPU kernel do not support memory slicing previously, but we fixed it in our compiler to generate correct kernels that support memory slicing. So this is a screenshot of the demo app that runs large language model on phones. We'll show it later. This is our evaluation. We tested our technique on various devices, including the latest iPhone and older generation of iPhone and iPads. And we also altered the number of stages we used to partition the model to see which strategy could lead to the best performance. Here's the results. So for iPhone 17, the best config is partitioning into 4 stages, both on Q134B and on quantized Q13414B. On other devices, on Q134B, the best config is A stage, and on quantized Q13414B, best config is A stage and 6 stage. We also looked into the profile results of a single decode iteration. For the Q134B model, computation takes only 2% of time. The weight loading takes almost 98%. This means that even if we do not do computation, that we still need 5.52 seconds to do one iteration. So even if we wanted to overlap the computation and memory and the weight loading, it actually does not produce any speed up. So we decided not to do it. We also checked the loading bandwidth, 1.45 gigabytes per second. It's very close to the theoretical bandwidth of the iPhone 7 Pro Max flash storage. Next, we do a live demo of the app.
Okay, so here is the latest iPhone 17 Pro Max model, and here is our app, which is named MLC Chat. So opening the app, we can see a series of models. We have 2 different models, QN4 billion and QN14 billion. Each of the model, we support different numbers of stages, from 2 stages to 8 stages, and we can arbitrarily open a model, and it will start with initialization. After the initialization, we can type the prompt. So we can ask a prompt, for example, like where is CMU, be concise. So after that, it will start to respond. The model tends to answer a lot of things, so we add the prompt of be concise so that it doesn't generate too much. And the overall generation speed, according to our evaluation, is about 4.5 seconds per token, and this is decently revealed in the actual speed that you can see, and it will say like CMU is in Pittsburgh, probably Pennsylvania next, and We just need to give it a little bit of patience and for it to complete the generation. It will generally take, given it is 5.5 tokens per seconds per token, if it's say 15 tokens or so, it would probably be more than 1 to 2 minutes. For this one, it's relatively concise, so we can see from the screen that the prefill speed is 0.4 seconds per token, which means the prefilling stage is very fast, and the decoding stage is 5.55 seconds per token, and the end-to-end total time is 50 seconds. And this is the demo of our application. Thank you.